Yeah, so let's look at that problem from week 8 first. This was the problem specifically. Uh, Problem from week 8. Yeah, so the problem is that two matrices P and Q are two cross two matrices which satisfy this relation. Now, last week I was trying to solve this problem in a little bit more generality, where I was trying to say uh, what we can say about the two matrices P and Q if they are in general n cross n matrices. Now, I still do not have the solution to that. What can we deduce if they are n cross n matrices? But for two cross two matrices, it's probably easier to answer. So a couple of things um, can be immediately deduced. Um, the first is that the trace of P is equal to 0, because the trace of P is equal to the trace of PQ minus trace of QP, and uh, trace is basically the trace functional uh, distributes over matrix sums and matrix multiplications. And so the trace of this quantity is equal to 0. So trace of P is equal to 0. So this is the first thing we can deduce. Um, the second thing that we can deduce over here is that um, right. So uh, P cannot be a full rank matrix. So the second thing is P is not full rank. Just give me 1 second. I have to reply to a message. Uh, okay, so P is not full rank. So why is P not full rank? Because let's say if P were full rank, um, then we get the following basically. We get P minus uh, PQ is equal to minus QP, right? Um, or okay, or rather we can write P plus uh, P plus QP is equal to PQ. Now let's multiply on the right hand side with P inverse so that we get 1 plus Q is equal to PQ P inverse. Right. Now, the problem with this kind of a relationship is that uh, if P is full rank, then the eigenvalues of so basically P Q P inverse is similar to Q, which means that the eigenvalues of this are equal to the eigenvalues of this. But the eigenvalues of 1 plus Q uh, is basically equal to all the eigenvalues of Q plus 1 added to it. Right. So, so even though they're real matrices, you can always consider complex eigenvalues of P and Q, and you basically arrive at this contradiction. So this gives you a contradiction. So P cannot be um, full rank. Okay. Uh, so these two statements are statements which you can obviously state for all n, for all uh, n cross n matrices. Now here we have to now deduce something about P and Q. Um, so let's uh, so what we can do is we can set this P. Um, yeah, so let's set this P as some equal to uh, some A minus A, B, sorry, B and C. Now, P is not full rank, so uh, one column has to be the a linear multiple of another column. So you can set this B comma minus A as equal to some alpha times A comma C, which if you substitute back, you get P to be equal to A minus A, uh, B is equal to alpha times A, and C is equal to 1 by alpha times A. Uh, so that makes it equal to A times uh, 1 alpha, alpha inverse minus 1. Okay. Alpha is a scalar, of course. Let's say alpha is not equal to 0. We're basically analyzing this case by case. Um, so now we have this going on 1 alpha, alpha inverse minus 1 times q uh, minus q times 1 alpha, alpha inverse minus 1 is equal to 1 alpha, alpha inverse minus 1. There's an A, but the A has got cancelled both sides. Okay. Again, we're assuming here that A is not equal to 0. So let's write this Q as equal to Q1, Q2, and okay. Just give me 1 minute. Uh, I think the answer to this is P squared is the answer C, uh, but I don't really know. If you're familiar with the solution, then uh, so one way to argue this is going in a different direction. Uh, so one way to argue it would be like this. So let's say you write P, um, just give me 1 second. Yeah, okay. The solution is given here. Um, okay. Um, I'm just reading out the solution given by the SWAM people. Um, yeah, it's an interesting solution. Uh, yeah. Okay. So this is the solution. Yeah. So the solution is as follows. I'm just copy pasting the solution from the portal. Um, so yeah, trace of p is equal to 0 as we deduced, and so which gives this thing as p squared is equal to minus determinant of p times I. Now the question is, of course, what is determinant of p? Right. This, of course, is clear. I hope this is clear why. The trace of p is equal to the sum of the eigenvalues of p, and the determinant of p is equal to the product of the eigenvalues of p. So uh, you can always write the characteristic equation. Uh, the characteristic equation can always be written as some x minus lambda one times x minus lambda two. Okay. Um where lambda 1 and lambda 2 are the eigenvalues of this. So if you write it in this way, lambda 1 plus lambda 2 is equal to trace of p, and lambda 1 times lambda 2 is the determinant of p. So this relation is clear. Now, the trace of p is equal to 0, which gives p square is equal to this. Now, you can write this p square in two different ways. So you can either pre-multiply with p, or you can post-multiply with p, which gives us 2p square is equal to p square q minus qp squared. Right. But each p squared is equal to minus determinant of p times I, and so this gives us to be equal to 0. Right. Um, yeah, so 0 is the solution. It's an interesting problem, of course. Um, it's interesting because it's kind of restricted to dimension 2. In higher dimensions, this argument would not necessarily hold, but it's an interesting problem for sure. Okay. The learning for me
Right,
also.
for 2 by 2 matrices, is
Yes.
it true that if p square equal to 0, that implies p equal to 0?
No, in
Is
this case, p
that
has to
true
be
for
equal to
all the
0. Yeah.
matrices of 2 by 2 matrices?
Yes.
Do
P
you have
has
any
to be
like
equal to 0 for this relation.
do you have
Sorry,
any
go on.
like results or like proof or something, result or theorem or something like related to that?
Related to which? Related to what? Uh,
That if p is a 2 by 2 matrix, then p square equal to 0. That implies if and only if p equal to 0 like that.
no. That's not necessarily true. If you have a matrix P, in general, let's talk about an n cross n matrix. Uh, P squared equals 0 does not necessarily imply that P is equal to 0. Okay. Um, you can easily uh, concoct some examples. So you can you can create an example like this, for instance. So let's say
No, it is
you
like
take
problem. Yeah, but anyway, this is one approach, but I don't know maybe how the participants can think. You should use the trace concept and then
yeah, that's why it's a difficult problem. Even I wasn't able to solve the problem, and it's a yeah it's an interesting problem. There are multiple concepts there. which have to be put together to solve this problem. First,
Maybe
the first,
that you are the only one who is preparing the question papers and all. Maybe we were saying you were not able to solve. I
no,
thought maybe
I do not prepare the
one
question. No, 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 no.
that's only key for this
The question.
answers.
No, 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 no. I do not prepare the keys for this. For this. Okay.
Okay.
The key. See, the course is a rerun from some of a previous course. Okay,
Yeah, yeah.
and the questions and the lecture videos are probably set up by the same professor who teaches this course. So
So
it's set up by him. Yeah, I do not. I do not either set up the questions or provide the solutions.
okay.
I'm only here as like an assist to essentially assist in doubt clearing and giving hints to solve problems. Maybe adding something more like how to solve a problem in some greater generality, that kind of thing. So yeah, I was trying to solve this problem for n cross n,
Hmm.
and the way I was looking at this was like a fixed point theorem problem. So a fixed point theorem is basically this, where you have a map uh, f from some space x to some space from x to x only. A fixed point is a point p such that uh, such that fp is equal to p. Okay. Now, now one way to look at this is a fixed point of a matrix map. So the matrix map is basically this. R 2 cross 2 to R 2 cross 2, which takes a matrix P and sends it to um, PQ minus QP. Okay. And so this matrix P is a fixed point of this map because you have P to be equal to PQ minus QP. Okay. And of course, if you now you can do two things. So you can do P squared is equal to P. So if you multiply from the right, so you get PQP minus QP squared. If you multiply from the left, you get P squared Q minus PQP. Sorry, minus PQP. So you can add both sides and you can get 2P squared is equal to P squared Q minus QP squared. Okay. So it's yeah, yeah. So yeah, and likewise, you get probably something like mm, yeah, and I think you can build like a tower like that. Uh, yeah, but yeah, it was not clear to me how to solve this problem. So yeah, so this is the solution. It's a slightly advanced problem. Okay, so you asked that if p square is equal to
Okay.
0, then p need not be equal to 0. All right. And a simple
Yeah.
counter example would be like this. So let's say you fix two bases E1 and E2. You set P E1 is equal to E2, and you set P E2 is equal to 0. So this is a rank 1 matrix. If you write this matrix P, if you write this linear map P in a matrix order, this will look like this. This will look like hmm, okay. And of course, you will see that p square is equal to 0, but p is not equal to 0. All right.
Uh,
So
Please look at
let's.
the second problem in the same assignment. Second,
Okay.
second problem in the same assignment.
Yeah, yeah.
Yeah, that's true. That's true.
Yes, yes, yes. Yeah, we had this discussion last time that um like the second problem, options A and B are identical, right? I mean, in that case, both would be correct, right? If either A or B
But
is true, then both should be correct, right?
because they, they
Some
said they said they have resolved, but they have not changed the
uh,
they have not changed the marks. But they are claiming that
oh
they have solved that question. They have
ah
resolved the
okay
ambiguity,
ah
but they
okay.
have
So
not changed the marks.
do you want me to write to them? Do you want me to write to them?
So I want
Yeah,
to know because they are claiming they have resolved.
maybe if possible, you can do that, Amrit, because most of
Yeah.
the even I selected a second option.
Hmm hmm
Then my marks
hmm.
also got affected.
Right. Right, right. Okay, I will report to them. I'll report to them. Uh,
So
I have no
how
way
can
to directly reach
we
out to the
if we
yeah
have any queries? How can we approach the team, like discussion forum, through discussion forum or
through discussion
some?
form. Yes. Otherwise, leave it to me. I will reach out to the NPTEL team
Okay,
and
okay.
I'll ask them to um, like they would know what who are the right people to reach out to because the so there is a programming inside the codes. The program is set to accept option A and reject all other options. So they would have to change the programming. Basically, the automated marking system that is there that has to be updated. So even I don't know who are the right people to reach out to, but I will ask some of the people, and then they might help me.
Yeah,
So,
yeah, please.
okay, let's hope let's see if we can resolve this. Okay,
Okay.
so let's look at week 9. Uh, um, so before directly jumping into the questions for week 9, I'd want to briefly look at the theory in week 9. I think it's um, before directly jumping to the problems. So in week 9, so there were two things mostly covered. So one was
That
the
that would be
um, yeah, sorry, what?
good. That would be good. Yeah.
Okay. So there were two things mostly covered. So the first thing is the SVD, and the second thing is some low rank approximations. Okay. Uh, so let's briefly look at the theory of this, and then we can look at the solutions. I guess once we understand the theory well, I've looked at the problems. The problems seem to be directly following from the theory. They don't seem very tricky. Okay, so the first is SVD. So in SVD, it stands for singular value decomposition. Uh, I'm going to kind of explain this in a slightly more theoretical way. So it's going to be a slightly different flavor from the notes, but it's going to be more or less the same. So you are given two finite dimensional vector spaces, U and V, okay, and you're given a linear map from U to V. Now
Also, uh,
the
just 1 minute. Sorry for the disturbance. Yeah, if you can, if you could give some applications of this before starting the
yeah,
concept. If you could
okay, okay,
give some applications of this concept where this singular value is uh,
haha,
used or right,
yes, 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 yes.
especially in
Okay,
computer science.
so okay, so let me first state what is singular value decomposition, and then let's And then let me first state the statement of singular value decomposition. And then let's look at some of the applications before looking at the proof of the singular value decomposition. So the statement is as follows. The statement is that uh, if you uh, if you have any such representation, if you have any such uh, linear map from U to V, okay, then uh, then there exists these okay, let's not use U and V. Okay, let's use X and Y. There's a reason why. Uh, let's say X and Y are two finite dimensional vector spaces, and T is a map from X to Y. Then uh, we can find an orthonormal basis for X and an orthonormal basis for Y. Okay, so this orthonormal basis for X, I'm going to write this as a matrix V. So V, so let's put dimensions over here. So let's say X is an n-dimensional space and Y is an m-dimensional space. So we have over here a matrix V, which is an orthonormal basis for X. So it is an orthogonal matrix of uh, uh, dimension uh, n cross n. Right. So V is an orthonormal uh, basis for V for X, right? And U is an orthonormal basis for Y. Okay. So what we want to so what the statement of SPT tells us is that we can find uh, we can find scalars uh, sigma 1 up to sigma r, where r is the rank of T, such that if you write this V as equal to some V1 to up to uh, Vr, then you write this as Vr up to some Vn, and you write this U as equal to U1 up to some UR, and then UR plus 1 up to some UM. Uh, then T of V1 is equal to, sorry, T of Vi is equal to sigma I times Ui for I from 1 to up to R, where R is the rank of T. Now, so essentially what it is telling me is that, so you know that if you have any linear map, so for now we are very commonly dealing with matrices, but it's also sometimes useful to look at these matrices as actually representations of linear maps. So if you have any linear map, you can represent it as a matrix once you fix bases called the domain and the codomain, right? So what this tells you is that you can fix a basis for X, or rather you can find a basis for X and you can find a basis for Y, such that in that basis, T looks like a diagonal matrix. So let me just write down a meta statement, which is that we can find uh, orthonormal uh, basis uh, for X and Y, such that in that basis, T is a diagonal matrix. I hope I hope the meaning of this statement is clear. such that in that basis T is a diagonal matrix. I hope the meaning of this statement is clear. Okay, so so what are some of the uses of this singular value decomposition? The first use of the singular value decomposition is that the singular value decomposition is the practically used way for determining the rank of a matrix. Uh,
Is
if
uh,
you're
uh,
given, yeah,
excuse me, Amrit.
yeah,
That as you can orthonormal basis for x and y. Is there any
yeah.
reason for considering this orthonormal basis so that T becomes diagonal matrix, or is there any reason?
Is there any reason? Are you asking reason?
Yeah. Is there any like?
Yeah, yeah. Yeah. The reason, no, I've not even proved. Like, I'm not giving a reason how we can compute it. I'm just telling this the statement of SVD, and the statement of SVD tells us that we can. So let's say there was no orthonormal. Assume that the word orthonormal was not there. Then the statement would
Yeah.
read like we can find basis for x and y, such that in that basis T is a diagonal matrix, which is fine. But when you write orthonormal, you are saying you are actually strengthening the statement. You're giving more information in that statement, where you're saying that not only can we find basis for x and y, but actually these bases would be orthonormal bases also. Okay, so it's a much more stronger statement. um, because once you include this orthonormality, uh, uh, you're also telling or stating some things related to the inner product of the spaces, right? So it's obviously a stronger statement. Now, as I said, one of the uses of the singular value decomposition is that it is the practically used method for determining the rank of a matrix. And this is one. And the other is, of course, there are many uses of the singular value decomposition, which is that once you have a linear map T, right? So you have this linear map T, and you want to make a proof. You want to prove some things about that linear map T, which let's say you want to prove some abstract statement about this linear map T. So one thing that you can always do is you can assume that not assume, uh, you can always take this T to be in a canonical form. So the canonical form looks like this. So T, you can always write this T as equal to U sigma V transpose. Okay, so this is like a canonical representation for T, where this sigma is a diagonal matrix of the singular values, and U and V are basically called the singular vectors of this matrix T. And once you assume this, and once you take T to be of this particular form, then you can actually make a lot of statements, because now you have a very nice handle on the matrix or on the linear operator, because you can because U is orthonormal, because U is the orthogonal matrix. V transpose is also an orthogonal matrix, and this is a diagonal matrix. So you have a lot of control over what statement you want to make. So in an abstract sense, a lot of statements and theorems can be proved from this particular representation. So one representation, so one proof that follows from here is the following facts, that if we have any if we consider um, the two norm of matrices. So let's say you want to compute this, which is defined as 2 uh, x belonging to 1 tx 2. Now, in general, if T is not a diagonalizable matrix, you cannot say too many things. But this statement holds for any matrix. This doesn't have to be a diagonalizable matrix. So if you so you can write this. this thing, uh, if you take square of both sides, then this is equal to uh, tx, uh, or this is equal to tx transpose times tx divided by x transpose times x. And there's a soup over that. So let's plug in some values. Um, this is equal to x transpose. Uh, you take the transpose of this as equal to v sigma uh, u transpose uh, u sigma v uh, v x divided by x transpose x. Right. Um, so you write this in this way.
Yeah, x transpose v sigma square. I think vx, not v transpose x.
Hmm?
That after the second step, x transpose v
What?
sigma square numerator.
Uh, numerator.
Yeah. And the
Yeah, there is a v transpose here. Yeah, there's a v transpose here. So
yeah,
yeah, it's
that's what it is.
u. Yeah, yeah,
Yeah,
yeah.
u
Basically,
transpose.
this.
That's u transpose. Yeah. Now in this case, correct. Yeah.
Yeah, yeah. U transpose u will become equal to one because it's an orthonormal matrix,
Yeah,
and
it's
you
an
get
orthonormal
this
basis. Yeah.
right, and uh, and you can then write this x transpose x is equal to x transpose v times v transpose x, and so if you write this y as equal to uh, v transpose x, then this form becomes equal to y transpose sigma squared y y transpose y. Okay. Uh, right. You can always write this as this. This is an orthonormal basis. So this is like a change of basis operation. This is writing. This is basically writing x is equal to vy. So it's a change of basis operation. And so then it's clear that if you want to get the supremum, then you look at this basis this diagonal matrix sigma. So sigma would look like something like this. Uh, it would look like some sigma 1 square, sigma 2 square, up to some sigma r square, and then there would be zeros. Okay. So you look at this diagonal matrix and you pick the one with the highest diagonal entries. So essentially, you pick the highest singular value. So and from there we get that the two norm of the matrix is basically this would be the square of the highest singular value. If you take square root, so we get that the two norm of any matrix is equal to the largest uh, singular value of p. So it of course gives you a very nice way of actually computing the two norms, right? Of course, you can compute the two norm as in an analytical way. Of course, the
Yeah.
you want to compute if you can compute
Can you
this
can,
max of
can you yeah, please,
huh?
don't mind. Can you repeat once again? Well, this two norm is equal to maximum largest singular variable. Please.
Yeah,
Can you
yeah.
repeat
So
one?
So you can write this as equal to this, right?
Yes, yeah.
You can write this to be equal to this. So if you can write this to be equal to this, then if I tell you what is the largest value this expression can get, okay, the largest value this expression can get is sigma 1 squared.
I don't know
Where
maybe
sigma
that
1 squared,
after simplification we will get that. Then is that
right? So let's
y equal?
so let
I
okay
mean
okay.
that is
So
matrix entirely this form or sigma form are different. I don't understand. From that form, how can we get
okay,
largest sigma?
let me break it down. Let me break this down a little bit. Okay. So so there are a couple of things that you have to. I have jumped a couple of steps. Okay. So the first thing is that so V is an orthonormal matrix. So what happens to orthonormal matrices? So you have to understand that orthonormal matrices produce isometries. Okay. So uh, in other words, if you do Py, sorry, uh, in other words, uh, if uh, if um, if x norm is equal to 1, then Vx norm is also equal to 1. This is clear, right? So this y that you're seeing over here, if I write this x as equal to v times y, then the norm of x is equal to the norm of y. Norms do not change if you multiply with an orthonormal matrix. Orthonormal matrices are what we call isometries. Why is it isometric? Why is this an isometric? Because Vx comma Vx, if you take this square, then this is equal to if you know the idea of an adjoint of a matrix, so this is equal to V star Vx comma x. Now this V star, what we write as the adjoint, is basically equal to V transpose X. But V transpose times V is equal to 1. And so this is equal to X times X. So this is called the adjoint of a matrix. Adjoint of, and this adjoint of V, so if I ask you what does this adjoint of V look like? The adjoint of V is equal to V transpose if, yeah, if this linear map if this linear map induced by V is expressed in orthonormal is expressed in an orthonormal basis. If you do not like this kind of an abstract argument, just this is it true for in general for inner product spaces, but since we are dealing with Rn, so don't have to worry too much. If you just write Vx comma Vx, this inner product, well, this is just equal to Vx transpose times Vx. This is how the inner product in Euclidean spaces is. So this is equal to x transpose v times x. So that is equal to x of x. This. So basically, the fact is, if you take any matrix, if you take any vector y and multiply it with an orthonormal matrix, it does not change distances, right? So here, when we are computing the soup of this thing, we do soup x uh, equal to 1, this quantity, right? This is so because you have, so now what I've done is that I've done a substitution of variables. The variable that I've substituted over here is that I have put x to be equal to vy. So if I put x to be equal to v times y, then notice that if x is on this unit circle, so x is on this unit circle, then y will also lie on the unit circle because v is an orthonormal matrix. And so this expression is just equal to soup of y norm equal to 1, this quantity. So now if you now this it's trivial to prove that uh, like okay, so what do you want to do? So if you write this y as equal to some y1 up to yn, if you write it like this, then then what is this expression equal to? This expression is equal to sigma 1 squared y1 squared plus sigma 2 squared y2 squared plus dot 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 divided by y1 squared plus y2 squared plus dot dot dot. Okay, so now this y1 squared plus y2 squared up to is equal to 1 because that is the constraint that you are dealing with. So this quantity is equal to 1. And so you're left with some sigma 1 squared y1 squared plus sigma 2 squared y2 squared and dot dot dot. So if you want to maximize this quantity, what will you do? You will set this y1 to be equal to 1 and you will set all these quantities to be equal to 0. So you're basically assuming that sigma 1 is greater than or equal to sigma 2 is greater than or equal to and so on. So if you want to maximize this quantity, you will set all these to be equal to 0 and you will get this to be equal to 1. These y1 squares are basically fractions. So the maximum value would be equal to sigma 1 squared. Right. I hope it's clear how you're getting this. Is it clear, right?
Yeah, it's no, it's clear.
Okay.
And can you give some
So,
applications, like in computer science or
I haven't even, yeah, so okay. So this is a very good application where you can compute the two norm of any matrix using the singular value decomposition. So
I
this is
think it's
one. The
in
second,
real life example,
huh?
maybe it's mathematically it is okay. It is one application.
Oh, okay, like a real world example.
Real world. Actually, I have seen that this singular value has one applications in recommendations, like
Oh,
in OTT platforms like Netflix or Amazon Prime.
ha 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 ha. Yeah.
There are many
So
options to choose the
okay, so
movies.
one application is as follows. So one of the applications is as follows. So hmm,
Yeah, yeah, you can.
okay.
Similar to that,
So
we have a share.
yeah, it's kind of going in a different tangent. So let me first let's do one thing. There are others in the course also. So let me first finish
Yeah, that's
today's
fine.
materials, and then let's
Yeah,
leave like 5-10 minutes to have this discussion. Okay. Um,
okay.
Right. So, so the statement of SVT is this. So one of the statements is you can compute the two rank. Let's first give some mathematical proof, mathematical applications. So first is you can get compute the two rank. The second is you can compute the rank of any matrix. This is the most practically used way to compute the rank of a matrix. Uh, that is one. The other is something called a low rank approximation of a matrix. So when we talk of a low rank approximation of the matrix, so let's say, and this kind of leads into what you were saying that if you have a linear map, uh, if you have this linear map um, from uh, some space to another space, uh, let's say you know that uh, that there is uh, okay. So let's say you can compute the singular values of t. So let's say the singular values of t are equal to some sigma 1, sigma 2, up to let's say some sigma k, then some sigma k plus 1 up to sigma n. Okay. Now assume, now let's say that, um, um, let's say um, that um, sigma 1 to sigma k are large and sigma k plus 1 up to sigma n are small. Okay. So let's put some concrete examples. So let's say uh, n is equal to 1 million. Okay, n is equal to 1 million. So it's a very large space. Uh, it's a space from 1 million dimensions to another space. These often happen in a lot of data science applications where you may be dealing with the data which has very large dimensions. Okay, so an example of that would be something like images. Okay, so if you can take an image, again this is slightly going off the territory, but let's say since I've started talking, so let me just finish it. So one way in which it's used in data science is that you can take an image. Okay, so an image is often represented as a set of pixels. Okay, it could be a 2D image, it could be a 3D image. So let's say it is a 2D image. It could be, let's say, something like a 1020 cross 1020 pixels. So then essentially, so each pixel is like this. So think of like a square grid of dimensions 1020 to 1020. Inside each cell of this grid, there is going to be a number. Okay, so that number is some RGB value, uh, which is some color value. Okay, so it basically tells you what is the color intensity in that pixel, and that's how all images, at least all colored images, are generated. If it's a black and white image, then you would have like a single value called a grayscale, where that number indicates whether if it's a large number, then that pixel is black. If it's a small number, then that pixel is close to white. Okay, so so now what happens is that you have this large 1020 cross 1020 image. Okay, now, one way to often deal with this is that you can sort of think of this image as a matrix. Okay, a matrix of dimensions 1000 cross 1000, and or 1020 cross 1020. And if you want to, you can do something called an image compression. So if you want to compress the image, one thing that can be done is you can compute the SVD of this matrix, and you can store a low rank approximation of this SVD of this matrix, and uh, in a lot of these image compressions, which you will see, there's a lot of applications that do these image compressions. Their SVDs can be used to compute a low rank approximation. Um, so yeah, that is one of the real world use cases of it. Uh, before going any further, let's just quickly see how you get. So you can get the this is basically the proof of SVD. Proof of SVD. So SVD basically tells you that you can take any matrix A, and let's say um, A is some M cross N matrix. Then you can write this A as equal to uh, U sigma V transpose. Okay.
where U and V are orthogonal and U is a matrix of order m by n and V is a matrix of order n plus n.
Yeah. And sigma D, these guys. So the proof of this is as follows. Uh, um, uh, consider uh, consider the linear map A transpose times A. Okay. Now A transpose times A is a symmetric matrix. Uh, it's a symmetric matrix, and one other thing is that the rank of A transpose A is equal to the rank of A. Uh, why? I leave it to you to prove this. This is left as an exercise. Okay, this is this can be easily proved. Okay, now
Maybe
so
I get
because
values, I guess.
no, you don't need eigenvalues. What you need is basically as follows. You need to prove this, that the null space of A transpose is equal to the range of A orthogonal, is the orthogonal complement of the range of A. You need to prove this statement. Null space of A transpose is equal to the orthogonal complement of range of A. Okay. And that is the reason why this rank of A transpose A is equal to rank of A. Because anything in the range of A does not get filled by A transpose. Because what are all the elements that get filled by A transpose lie in the orthogonal complement of the range of A. So A transpose of AX is equal to 0 if and only if AX is equal to 0. Okay. It's precisely because of this fact. So you need to prove this fact. And in order to prove this fact, it's kind of useful to use. It's kind of useful to think of A transpose as being an adjoint, and kind of looking at this adjoint relation where AX comma Y is equal to X comma A transpose Y. Okay, so that's how you prove it. Um, Now, this A transpose A is a symmetric matrix. It's a real symmetric matrix, and real symmetric matrices always have non-negative eigenvalues. Okay, and not only would they have non-negative eigenvalues, but the eigen vectors but the eigenvectors that correspond to distinct eigenvalues are orthogonal to each other. So, in other words, the eigenspace that corresponds to distinct eigenvalues are orthogonal to each other. So, what this means in general is that you can for a real symmetric matrix. So, let me just write down for a real symmetric matrix. We can uh, we can get uh, we can get a basis. We can get um, an orthonormal basis uh, of eigenvectors. Okay, so let's say we have got such a basis. So let's say A transpose A V. So let's say V1, V2 up to some Vn uh, is such a basis. So so the thing is this. If you look at the eigenvalues of A transpose A, let's write that those eigenvalues as equal to some uh, let's write those eigenvalues as equal to some sigma 1 squared up to sigma r squared, and then the rest are zeros. Okay, because the rank is r, the other guys is 0, and the rank of A transpose A is going to be equal to the rank of A, right? So this A transpose AV, and let's write this. Let's put it like this. Let's write A transpose A times V1 is equal to some sigma 1 squared times V1. Okay. Okay. So now let's put U as equal to, let's put U1 as equal to AV1. Okay. Then what is U, or let's just say UI is equal to AVI. So what is UI times UJ? The inner product of UI times UJ, that is equal to AVI times AVJ, that is equal to A transpose A times VI times VJ. And so this is equal to 0 if I is not equal to J. And if I is equal to J, then Vi is an eigenvector of A transpose A. So that is equal to sigma I squared, right? Uh, if I is equal to J. So if you consider this matrix, if you consider this set of vectors, Ui times sigma I inverse, if you consider this collection of vectors, then this is an ortho. This uh, is an orthonormal basis, or rather, this is a yeah, this is an orthonormal basis because now if you do this inner product of this thing, then the sigma I squared will get cancelled and you get one. So you'll get an orthonormal basis. Uh, so so now what you can do is you can write this uh, a v uh, a v I as equal to, so what is AVI? AVI is equal to this UI. This is by definition, AVI is equal to UI. So this I'm going to write it as equal to sigma I inverse times UI times sigma I. Okay. Uh, this collection of vectors is an orthogonal. I've been saying this is an orthogonal basis, but I haven't written what is. I have to be a bit more precise. I should say this is an orthonormal basis for the range of A. This need not be an orthonormal basis for the whole codomain of A, because if the rank of A is smaller than the rank of the codomain of A, then this is obviously not going to be an orthonormal basis for the whole of this thing. But what you can always do is that so basically from this expression what we get is that if R is the rank of A, then I can find these vectors AV1 equal to this UI dash. I call this to be equal to UI prime times sigma 1. And I get this up to AVR is equal to UR dash times sigma R, where uh, where UR dash is equal to sigma, or rather I dash is equal to sigma I inverse of AVI. This is for I from 1 to R. Okay. Now, what we can always do uh, uh, is that we can adjoin some extra vectors, right? So we can add a few extra vectors which correspond to the null space of of A, and you can add those guys. So you can write A VR plus 1 is equal to 0 times. Uh, uh, so these UI dashes, you adjoin some extra vectors over here. Uh, u r plus 1 dash, and you can adjoin some zeros over here. Okay. So when you write this neatly as a matrix, what you get is as follows. You get A times V is equal to U times this sigma. Okay. And V is an orthogonal matrix. So you get A is equal to U times sigma V transpose. Okay. So uh, this is uh, uh, this is the SVD. The other thing that is going to be needed for this week is what we call the low rank approximations. Um, okay, so low rank approximations is basically saying this. So you are given a matrix A given A and some K. So K is a scalar. Uh, and uh, we want to find a matrix B. Assume that these are n cross n matrices. Okay. We want to find a matrix B n cross n such that the rank of B is equal to K and uh, A minus B uh, with respect to this Frobenius norm is minimized. Okay. Um, so essentially, we want to find the matrix B which is closest to A with respect to the Frobenius norm, such that the rank of B is K. So oftentimes what happens is that this number K is going to be significantly smaller than N. And so you get like a low rank approximation of A, approximation in the sense that it is closest to A with respect to the Frobenius norm. And so, and the proof of this is as follows. So, what should B look like? Um, so, right. So, uh, so what is the Frobenius norm of any matrix? So, if you give me any matrix uh, uh, Q, then the Frobenius norm of Q squared is equal to the trace of Q transpose Q. Okay. If you write Q as equal to some U uh, sigma B transpose, then the trace of Q transpose Q, jumping a few steps, so that would be equal to um, trace of V transpose sigma square B, right? And so this is that will be equal to the trace commutes, of course. So uh, V and V transpose is equal to 1 because this is basically the SPD of Q, and so that would be equal to trace of sigma squared. Okay. Now, how is this useful over here? So the so the observation is that if if B is closest to A, then um, then U transpose BV is closest to uh, U transpose AV. Okay, and again, it's the same thing. If you
Excuse
you do this thing, yeah. If you do A transpose U transpose AV minus U transpose BV, you take the Frobenius norm of this. Uh, that is equal to uh, basically is the Frobenius norm of U transpose A minus B times V.
complete.
Yeah, and this is equal to A minus B Frobenius norm squared. Yeah, tell me.
Yeah,
Hello.
previous this yeah trace of Q transpose Q. Can you go to that
Yes.
step?
Yeah. Uh, this step.
Yeah, मैं after simplification
Yeah, I mean just
after
substitute it. So
uh,
Q transpose times Q. Let me write it down. Q transpose Q is equal to
Yeah.
V sigma U transpose U sigma V. So U transpose times U is equal to
Oh,
identity, and
yeah,
and you get,
you can explain only the
yeah,
last
your
step.
voice is breaking.
So now can you clear now?
Yeah, now
Can
I
you hear
can
me?
hear. Yeah. So yeah, I can hear you
I
now. So this is equal
yeah
to V sigma squared V transpose. You're talking about this step?
yeah.
Yeah. So this is
La-
follows from here. Like trace of AB is equal to trace of BA. Trace of AB is equal to trace of BA. Okay.
Okay,
So
okay.
you can take this B and send it to this side.
Okay, I know
Right.
I got it. Yeah.
Hmm. All right. Yeah. So if B is closest to A, then uh, if you do this, if you do U transpose BV, then this is going to be closest to U transpose AB. In fact, the Frobenius norm remains unaltered if you do this. Yeah, if you pre-multiply and post-multiply by these orthonormal matrices. Okay. So how does this help us in computing uh, in computing this uh, in computing a low rank approximation? Well, just write A as equal to uh, U sigma V transpose. Okay. So then A minus B Frobenius norm square is equal to uh, sigma minus U transpose B B F square. Right. Uh, yeah. And um, and if you want this thing to be minimized, if you want like a rank K, uh, if you want like a rank K approximation of this, then uh, you should choose this uh, U transpose B V. So let's say this sigma is equal to some looks like this. Let's say sigma one uh, or to some sigma r plus two zeros or not zeros. Let's write it as sigma r1 plus square of two sigma n. Yeah. So then uh, um, right. So choose this. Just give me 1 minute. Uh,
Yeah, I mean, is that Frobenius norm of A minus B is equal to the Frobenius norm of sigma? Is that true?
sorry, what?
Yeah. You have written there A minus B of Frobenius norm is equal to sigma minus U transpose B. How we have written?
This statement, this line,
Yeah.
this
Yes. Yes.
line.
Yes. Yeah.
Yeah. This follows from this line. Right? A minus B Frobenius norm is equal to U
Yeah.
transpose
Now A
AB
minus B.
minus U transpose BB.
Yeah.
Now uh, if you do U transpose, okay, what is U transpose AB? That is equal to U transpose U sigma
Okay.
V transpose B.
I understand. Yeah.
Okay.
from that, maybe it's steps are clumsy. Like what's explaining something one way and or writing one way. It's not that much clear. That's why.
Yeah, I am jumping a few steps. We're kind of running out of time, so that's why I've jumped a few steps. Um,
It's
okay,
not like if you can
so
explain through in a sequence manner, it would be good for us.
okay,
No
just
problem.
pay a little bit close attention. Sometimes I deliberately jump steps. I mean, jumping steps is not good, but it's not bad also, because what it does is that it keeps you it keeps you it forces you to pay attention, because I'm deliberately jumping steps here and there.
Yeah, the problem is
Um,
here. Yeah, the problem is we are new to this course, especially this low rank approximation and all. Even I haven't watched the videos,
hmm.
so
Okay,
I'm
okay.
really
So
in this. So for
yeah,
so,
yes.
for
So okay. So to summarize this thing, uh, this Frobenius norm is going to be minimized if B uh, if if U transpose BV looks like this. B has to be rank K matrix. So I'm going to choose the first K singular value. So the singular values are always arranged in from the highest to the lowest. Okay, this is highest to lowest, highest to lowest. And so what I'll do is that I'll choose this U transpose BV to be equal to the first K largest eigenvalues and then zero afterwards. So that would give me uh, a rank K matrix, which is going to be closest to this. There are a few steps which from here, like how you get from here to here, but you can look at the notes. I'm not going to I'm not going to prove that in detail. It's not needed also. So basically, what happens is that P is equal to U transpose this guy times V. So in other words, the way you get this low rank approximation is that you take A. So let me just write down the steps clearly. Uh, compute the compute SVD of A. Okay. Let A equal to U transpose sigma V. Okay. Set B to be equal to U transpose sigma K times V, where sigma K is this matrix. It is sigma 1 up to sigma K, and the rest of the entries are set to 0.
at
So
least
inside
here
this,
A is U sigma V transpose or U transpose sigma V transpose.
what? A
The
A
second
is
step
equal to, sorry. Yeah,
U.
yeah, yeah. I wrote it wrongly. U sigma V transpose. Yeah, yeah. I'm
Yeah,
sorry.
yeah,
Thanks for pointing it. Yeah, A is equal to U sigma V transpose, and B is equal to U sigma K V transpose. So you just look at this diagonal matrix and you take the first K diagonal entries of this diagonal matrix, and the others are set to 0. So this would give you the K rank approximation for A. This is how you're going to compute this. For this should suffice for most practical purposes. Okay. That said, let's uh, uh, I would encourage you to have a look at the notes. This is by no means an exhaustive coverage of the whole notes for this week. If you have any doubts, you can let me know.
I think
I've only
just one
covered
more
that.
just last query. Yeah, I mean here
Yeah,
in the slot.
yeah,
Uh,
yeah,
is what is sigma k is sigma 1 sigma 2 and so on sigma k. What about is that
yeah.
represents rank of A equal to rank of B or something? I think
No,
this last
I'm not talking about the rank of A. I'm not
okay.
talking about the rank of A. A is a
So
matrix that is given to you.
when we choose then
You
sigma
have to
A.
no, you have to compute a rank K approximation of A. So what you do is that you first compute an SVD of A. So this
Yeah,
is the SVD of A, right?
yeah, that we can do. Yeah.
You
Yes, yes.
yeah, you know the SVD of A. So you know this matrix here. So inside this matrix, if you look at this matrix, so this matrix would look like this. It would look like sigma 1, sigma 2, up to some sigma n. Okay.
Yeah.
Some of the entries towards the end could be equal to 0 if A is not a full rank matrix, but that should not matter to you. You look at only the first K diagonal entries
Only
and pick
first,
them.
only first K.
Yes, first K, because you want a rank K approximation.
Oh, rank.
So this is the rank.
Okay.
So let
Yeah.
me write it down over here. P
Okay. Okay.
is the rank K approximation of A.
Okay. Okay. Now I understand. Yeah.
So you have
Rank.
you can't pick more than
And
K. If you pick more than K, then the rank of
yeah,
B will become more than K.
yeah, definitely, definitely. Now I understood. Yeah. Yeah.
Yeah, so you pick exactly K. All
Yeah.
right.
Yeah.
So this should suffice for most computational purposes. This amount of theory should suffice. So let's look at the problems. The problems are easy for this week. So I'm only just going to go over them rather quickly because they're mostly computational problems. They're not like I didn't notice any tricky problems, but let's see. I may be wrong.
Is there any like shortcut way to construct this U and V, or like just compute the eigenvalues of
No,
A
no,
and
no. There is. I mean, for most practical purposes, in an actual problem, they will never give you. They'll, yeah, I mean, there is no shortcut way of doing it. You have to do A transpose A and then compute the
yeah,
eigenvalues of A transpose A.
it's like
Yeah, I
like
mean,
process.
yeah. I mean, if like no one does this by hand. This is not supposed to be done by hand. There are there are fast algorithms that compute these SVDs of A, and that
Oh,
also is computed in various ways. Like the
uh,
algorithms that compute SVD of A do not necessarily compute the eigenvalues, then the eigenvectors of A transpose A. No, it doesn't do all of that. There is
yeah.
an analytical way of getting it. And the analytical way of getting it is basically this. So as we described over here, that the sigma 1 is equal to soup of ax by x, right? In the 2 norm.
Hmm.
This is what we found out, right? So this is an analytical expression, right? You can technically differentiate this expression and get a maximum, right? That you can do that always. You can always differentiate this and get a maximum. So that would give you the largest eigenvalue. That would give you the largest singular value. Now, if you want to compute the second largest singular value, you put a constraint over here. So recall that when you're doing these singular value computations, the so you have these singular vectors v1, v2 up to so on, right? Where a v1 is equal to some sigma 1 times u1 and a v2 and so on. And but this v2 is orthogonal to v1, right? So next time when you compute this thing, you put this constraint over here. You put you sup of x norm is equal to 1, ax ax2 by x2. But you put a constraint over here. The constraint is as follows: you put x transpose v1 is equal to 0 because you want the next singular vector to be orthonormal to this vector v1. You want it to be orthogonal to this vector v1. So if you want this to be orthogonal to this vector v1, you put an additional constraint. And if you have done problems on constraint optimization, then you can use something called Lagrange multipliers. Lagrange multipliers can then be used to, again, you can solve this analytically. Uh, you can again solve this analytically. And likewise, when you want to compute, let's say, the kth eigenvector, then you solve this, but the constraints are as follows. You have x transpose v1 is equal to 0, x transpose v2 is equal to 0, and likewise, you have x transpose Vk minus 1 is equal to 0. You put this k minus 1 constraints to this system, and again you can solve this analytically. So that's often how this thing gets computed in practice. No one computes this by hand. The examples, the problems that will be given to you uh, should almost never require you to compute A transpose A and get the eigenvalues. There would always be some trick in that inside that problem that lets you quickly compute it. This is what you should always keep
Yeah.
in mind for the
Okay.
purpose of
Okay.
this course.
Okay. Okay.
Okay. Right. So the first problem is as follows. We have let RW know the rank of the matrix W. Then for W is equal to UV. Um, which of the following is true? What can we say about the rank of W? Uh, yeah, what can we say about the rank of W from the rank of U and V? So, yeah, I'm not going to solve this. This is a very easy problem. Uh, so I'm just going to move to the second problem. Okay. Uh,
I mean, do we need to use the properties of rank here?
yes,
I think.
this has nothing to do with this week. This is just from week 1.
Yeah, yeah, yeah. That's what I mean. Yeah, I think
This is
maybe
from week 1.
maybe I was confusing with this. Yeah.
Yeah, let me just write it down. Properties of rank. Use definition of rank. Just write it here. Use definition of rank of a matrix. Just to recall what the rank of a matrix is, the rank of a matrix is a dimension of a range. This is what the rank of a matrix. Yeah, use that definition to solve this. Second problem. The maximum singular value of A is okay. Um, okay, there's nothing to write prove over here. Okay, um, going on straight to problem 3. So let A be something like this. What is the closest rank 1 approximation of A in the 2 norm? Yeah. Okay. Yeah, I mean these matrices are not even rank 1 matrices. So there's nothing uh, to do over here. Okay. Let's look at the fourth problem. Yeah, I hope this is clear, right? These are straightforward problems. Right. So let A R cross N denote an invertible covariance matrix. Okay. Um, hmm, hmm, hmm. Okay. Then the direction that corresponds to the maximum eigenvalue is the direction of um, Okay, look at this problem. Hmm. Just give me 1 minute. Just give me 1 minute. I'll be back in 1 minute. Okay. All right. So we have this. Yeah, we have to use the definitions of variance correlation over here. Um, just give me 1 second. Let me quickly recall what are the definitions of uh, variance. This is slightly ambiguous as a question. It's not even strictly related to this course. Uh, this particular question. Um,
Does the lecture material
yeah.
contains any information about this question?
No, no, it does not. No, no, it does not have. Yeah, I don't think there is. Maybe the
Maybe
lecture videos have. The lecture material does not have. I haven't looked at the videos. So I mean, yeah. I mean, the direction of. Yeah, I'm not sure exactly. It just feels like a little bit. Um, I mean, it would have been better if they define what they mean by variance, correlation, etc. Just like that. Um uh, just like that is difficult uh, to say what they are trying to mean over here. So in general, if you have like a random vector over here, let's say x is a random vector, which means that there are these random variables x1 to xn. Uh, and if A is this covariance matrix, then is this n cross n matrix where Aij is basically equal to the uh, yeah, Aij is basically equal to the variance of xi xj. This is how typically a covariance matrix is defined. Now, um, now what they mean when they say the direction that corresponds to the minimum eigenvalue, uh, yeah, it's not really clear to me. Uh, uh, like my understanding tells me that the direction which corresponds um, to the uh, minimum eigenvalue should correspond to the maximum correlation. But I may be wrong. Let's look at this question next week. It's a bit slightly not related to the course. It would have been better uh, if they define what they meant by correlation, variance, etc. If you have any ideas, you can let me know. Otherwise, we'll move on to the next problem.
I haven't watched lecture videos and lecture. I haven't seen the lecture
Okay,
material also.
okay,
I
okay.
don't know about others.
Um, right. So this problem, yeah, it's given that A is equal to U sigma V transpose. Um, yeah, I mean uh, just unpack, uh, just express A in terms of this U sigma V transpose, and you'll arrive at one of the solutions. You'll arrive at the correct solution. That's how you do it. Um, okay. That's the sixth problem. Yeah. So this problem is that substitute A with U sigma V transpose. Yeah, this is a fairly easy problem. So from the definition of SVD, uh, this uh, the singular values themselves uh, are the eigenvalues uh, A transpose uh, of A transpose A, right? Uh, so, but this is just one thing that the singular values are the positive square roots of the eigenvalues of A. So you have to be careful with that one because the way we have uh, the way um, we wrote this was as follows. Uh, we basically wrote it like this. We recall we would have written it as A transpose A V1 is equal to sigma 1 squared times V1. Okay, so uh, so the singular values are the positive square roots of the eigenvalues of A transpose A. Okay, uh, so be careful which power you are dealing with here. The rest should be clear. Okay. Yeah, again, you have to compute the two norm of A. The two norm of A should be clear what the two norm of A is because A is already a diagonal matrix, and if you're given a diagonal matrix, the uh, then the SVD is very clear from the diagram. You know that the two norm would be equal to the similar value. Um, the next, the eighth problem is requires to compute the closest rank one approximation of A. Again, A is a diagonal matrix, so uh, this is a trivial computation uh, from what we have discussed uh, today. Just give me a second. Yeah, let's look at the final two problems. Yeah,
Excuse
which
me,
one of
Abhay.
the following is yes? Sorry.
I mean, is there any way to identify that the three pieces are not in singular value decomposition, not by doing calculations?
Oh, okay, okay, okay.
Like by looking at the
Uh,
three pieces, can we identify like Do you know any idea?
Yeah, you can always identify. Um, yeah, the um, yes, you can definitely identify. Um, uh, yeah, so if you're given this diagonal matrix, um, let's say you're given this diagonal matrix where you have A U1 is equal to some, or AUI is equal to some alpha I times UI. So the matrix is a diagonal matrix, uh, alpha 1, so on, alpha n, the diagonal matrix. Um, so the first thing is that the SBD always requires that the singular values be positive. Okay. So if any of uh, uh, this this alpha is negative, you can write it in this way. Write AUI is equal to um, uh, yeah, AUI is equal to uh, the sine of alpha I times mod of alpha I times UI. Okay, so this is equal to alpha I times sine of alpha I times UI. This is AUI, and so the so yeah, so one thing is that uh, uh, the SVD for a diagonal matrix uh, would always be uh, the eigenvalues, would always be uh, uh, right. It would always be the absolute values of the diagonal entries. Okay, so for instance over here this 0.5 comma 0.5, you can always uh, strike them off as being incorrect. Okay. Uh, the next thing, of course, you can look at uh, yeah. I mean, this is one way to write this eigenvalue, right? So yeah, the trick lies in this. So if you have this diagonal matrix, you're going to write A U I is equal to alpha I times sine of alpha I times ui. So for in this case, what you get, let's say the basis is given to you. The basis is, let's say, E1 and E2. So you have A E1 is equal to E1 and A E2 is equal to minus E2. Okay, so you're going to write it in this way: A times E1 E2. So E1 E2 is a vector over here, is equal to uh, E1 comma minus E2, and here you put 1 0 0 1. Okay, and then A is equal to E1 minus E2 1 0 0 1. uh, this E1 E2 is just the identity matrix. This is I 2 cross 2. So the SVD is always unique. Okay, the SVD is always unique. Uh, the only place where it can possibly be non-unique is when uh, hello, yeah, hopefully I'm
Yeah,
audible.
yeah,
Yeah,
yeah, yeah.
the way the SVD can be non-unique is when what are the singular values? The singular values correspond to, so the squares of the singular values are the eigenvalues of A transpose A. But the eigenvalues of A transpose A need not be distinct. So you can have one eigenvalue, which could have, let's say, the eigenspace that corresponds to that one eigenvalue, uh, maybe of dimension greater than one. So basically, that eigenvalue may be a repeated eigenvalue. So when that eigenvalue is a repeated eigenvalue, uh, then of course what can happen is that you can have a rearrangement of the rows and columns. So let's say, I hope what I'm trying to say is clear. So let's say uh, A transpose A times V is equal to lambda uh, U, and A transpose A times V tilde is equal to also lambda times some U tilde. Okay. So when you are going to write the SBD, so you are supposed to always arrange the SBD in a way that it goes from the highest singular value to the lowest singular value. But if you have the singular value which is repeated, then of course you can put V you can put V first and V tilde, or you can put V tilde first and then V. So, so what I'm trying to say is the SVD is unique up to the SVD is unique up to up to a transposition, up to a rearrangement or a permutation of the columns uh, and rows of U and V uh, corresponding to a repeated eigenvalue. Okay, I hope this makes sense. Yeah, hopefully this makes sense. What I'm trying to say. I if you have unique singular values, then it's going to be unique only.
Okay.
Okay, let's look at the last problem. Uh, right. So in this problem, we're given uh, and A is represented in this form. I hope you can understand what this form means. So this is the SVD of A, but the SVD of A is written in this particular. So A is written as a sum of three linear maps. Uh, this is one linear map, this is one linear map, and this is one linear map. So just to like break it down, if you write, let's say you have AV1 is equal to sigma 1 times U1, AV2 is equal to sigma 2 U2, and AV3 is equal to sigma 3 times U3. Let's say this is the SVD of A. Okay, basically you would write A as equal to U sigma V transpose. Okay, where V is going to be this V1, V2, V3, U is equal to U1, U2, U3, U3, and sigma is equal to uh, sigma 1, sigma 2, sigma 3. So this is the SVD. Then, if you consider this uh, linear transpose, this linear map, uh, right? Uh, sigma 1, U1, V1 transpose plus sigma 2, U2, V2 transpose plus sigma 3, U3, V3 transpose. Then notice that this map is equal to A. Okay. Why? Because if you put A times V1, then it's going to be equal to sigma 1 U1. Similarly, A V2 is sigma 2 U2, and A V3 is sigma 3 U3. You can just put the values over here. Okay, so and it says which of the following statements is false? Sorry. Um, First is read V2 V2 transpose A transpose times A is equal to A V2 transpose times A. Now A V2 is um, right. So A V2, what is A V2? A V2 is equal to uh, sigma 2 times uh, yeah, I guess you have to verify these options one after one by one. Um, okay, let's verify the first option. I'll let you verify the others. So A is equal to U sigma V transpose A transpose. So notice that this is the form that they have given, but I'm expressing it in this way because this is equal to this. Okay. So A transpose is equal to V sigma U transpose. So A
So how
transpose
can
A
you say that?
is V
Yeah.
sigma square V transpose, right? And then V2 transpose of A transpose A. Well, what is that equal to? So it is V2 transpose of V sigma square times V transpose. So V2 square times V is it's going to be equal to this. Uh, um, it's going to be equal to this row vector. This is going to be 0, 1, 0. Okay. Then sigma 2 sigma square times V transpose. So this is 0, 1, 0. This is going to be equal to uh, yeah. So right. So if you just multiply this with this, you get this to be equal to sigma 2 squared times V transpose. So sorry, not this. This is going to be 0 sigma 2 squared 0 times V transpose. So this is going to be equal to sigma 2 squared times uh, V2 transpose, right? So the first one is obviously correct. Uh, the second one, the rank of A is equal to 3. So this is also going to be correct. Um, yeah, like options, the false answer is obviously in options C and D. If you can correct it. You can check it for yourself. Okay. Um,
How we have written like so this problem. Can you go to
Hello.
the previous steps? Yeah, can you go to the previous
Which
steps?
which
The last one,
which
last problem,
problem? This
last problem,
problem?
last problem,
Yeah,
last 10th.
yeah,
Is equal to 0, 1, 0. It's like
yeah. Why is this equal to 0, 1, 0?
how we have to, yeah, yeah,
Yeah, yeah. So V is an uh, so this is the uh, so this is the SVD of A, right? So V has
yeah,
is V1, V2, V3. Okay.
yes,
So
yes.
when you do V2 transpose of V, so you're basically taking inner products of V2 with V1, V2 with V2, and V2 with V3. Okay. Now this is an orthonormal matrix, so that's why you get 0, 1, 0.
Okay, okay, okay. Okay. Maybe I think maybe differently. So here we are multiplying with V2 vector, no? Right. Okay, okay.
Yes, you are multiplying with, yeah, which is basically same as taking an inner product, and so you get 0, 1, 0. Yeah, the first option is
Yeah.
obviously correct. Yeah, the second option is also obviously correct, uh, because the singular values are said to be greater than 0, so it's definitely a rank 3 matrix. The false answer is in option C and D, which uh, I leave it to you to verify which of them is the correct option. Okay.
Yeah. Can you
All right.
can you go to the like fourth or fifth problem? Just
Fourth and fifth problem.
yeah, just fourth.
Yeah,
Yeah, this
fourth
one,
is
this
this
that
problem.
one.
I'm not sure.
Not
Yeah,
that, not
let's
that
look
one.
at this problem next week. Yeah,
Not that
and
one. Not that one.
fifth problem. Then which one?
Sixth one maybe. Yeah,
Sixth
just give
one.
some idea.
This
Just
one. Yeah,
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 yeah. So this one is like
yeah, yeah, yeah.
this one is you have to just substitute. So uh, just write A is
Give some
equal
hints.
to U sigma V transpose. Right, A transpose as equal to V sigma U transpose. Then A transpose times A is equal to V sigma squared V transpose, and uh, then you do A transpose A Frobenius norm, which is equal to uh, V sigma squared V transpose Frobenius norm. Okay. Now the now as I said, uh, uh, if you have these uh, yeah, the Frobenius norm is does not change if you multiply two sides with V and V transpose. Okay, because the Frobenius norm is defined as a trace. Um, so, I mean, if you have, if you're doing this thing, if you're doing uh, Frobenius norm of F, and if you're doing Frobenius norm of if you're doing Frobenius norm of some C inverse A C F, okay, then what is the Frobenius norm of this thing? The Frobenius norm of this is squared of this is equal to trace of C inverse AC. Uh, Sorry, there's a transpose over here. So let's write it as C transpose, and this is equal to uh, uh, C A C transpose times C transpose. So that is equal to trace of C A squared C transpose. So that is equal to trace of A squared. Okay. So that is equal to sorry, this
Yeah,
is
now I understand. Now I
this
understand.
A
Understand.
transpose here. So there is a trace of A transpose A. So if you have, so just recall, just understand that if you have if you take any matrix and if you and if you do this, you you do this V sigma squared V transpose, then the Frobenius norm doesn't change. The Frobenius norm of this is equal to the Frobenius norm of this thing, right? Now, now this is a diagonal matrix. So the Frobenius norm of this would be, well, it's just going to be equal to the sum of the, you know how, what is the definition of the Frobenius norm, right? And this is a diagonal matrix. This is the diagonal matrix of the squares of the singular values of A. So the correct option would be equal to A. Okay.
Yeah, would it be right? Maybe exact answer.
Okay.
I'm
I
just
think
checking.
our time is up. So let's meet next week. If you have any questions, you can ask me quickly. Otherwise, let's meet
Please write to us
next week.
the problem number 2 of assignment 8.
Yeah. I'll talk to them. Okay.
Thank you.
See you.
Yeah, thank you, thank you.
See you. Bye.
Actually, I have some more queries. I will discuss through WhatsApp maybe later.